All right, everybody. So we have just learned about polynomial inequalities, where we have a polynomial on one side of an inequality. Now we'd like to do the same thing, but for rational functions. And the steps are pretty much the same, except now, instead of finding just the zeros of the function at hand, we'll find the zeros as well as any point not in the domain. So in other words, this means for our rational function, we'll find the zeros of both the top of the rational function. This gives us the zeros itself of the function, and then also the zeros of the bottom, the denominator. Those will give us the points that are not in the domain. And so then all of those x values will go together to give us our sign chart, and then everything else works the same way from there. So we'll just do a couple of these, and we won't want this to go on too long. But yeah, I think we're going to probably also not really deal with the whole like graphical approach for these. We'll just kind of use these steps and just go forward from there. So the first one here is x minus 3 divided by x plus 1 is less than or equal to 0. When does that happen? Well, let's see. The zeros are when the numerator is equal to 0. So that's x minus 3 equals to 0. So that gives us x equals to 3. And the x values not in the domain are those for which x plus 1 equals 0. And so that just gives us x equals to minus 1. Okay, so we have two kind of x values of interest here. So that splits the real line into 3 intervals. So let's see. On the left side, the interval of x values less than minus 1, my favorite x value is minus 2. And if we evaluate the function that we have at x equals to minus 2, we get minus 2 minus 3 divided by minus 2 plus 1. That gives us minus 5 over minus 1, which is positive. So we will mark a plus sign for that interval. OK. In the next interval, we have the x values between minus 1 and 3. My favorite x value there is x equals to 0. So it's easy to evaluate, guys. It's 0, right? So we've got 0 minus 3 over 0 plus 1. That gives us minus 3 over 1, which is negative. So we'll put a minus sign here. That means throughout this entire interval, this rational function is negative. OK, and then last but not least, we'll have the x values that are bigger than 3. My favorite one is x equals to 4. And if we evaluate our rational function there, we have 4 minus 3 over 4 plus 1 equals to 1/5, which is bigger than 0. So that is a positive value. So that rational function takes on only positive values in this interval. The idea being is that we found all the possible vertical asymptotes and we found all the possible zeros. So the function can't behave anything other than being positive or negative away from there. So it has to be one thing, and it will stay that same thing until it would change by either having another 0 or another vertical asymptote. Well, we don't have any more of those, so we have to have this behavior for the rest of the real life. So it looks like we found the places where this function is negative. It's in between minus 1 and 3. But notice, they ask us actually for where is this function less than or equal to 0. And we have one other place where this function equals to 0. That is at x equals to 3. Notice that x equals to minus 1 is not a place where this whole rational function equals to 0, but rather a place where this rational function is undefined. So x equals minus 1 does not get to be included in our answer. So in particular, we get that the solution is the interval from minus 1 to 3, which includes 3, but does not include minus 1, since the function is undefined at minus 1, but it is equal to 0 when x equals to 3. OK. Let's move on to the next one. Let's see what's going on there. We have x squared minus 4 divided by x squared is less than 0. So we'll play the same game. We'll set the numerator equal to 0, and we get x squared equals to 4, which means x is plus or minus 2. And then we will set the denominator equal to 0 to get the x values not in the domain, and that gives us x squared is 0, which gives us just one value, x equals to 0. Okay, and so once again, we will split the real line into the now 4 subintervals that we get from these 3 x values of interest. And in the, I want to notice here that there's a little bit of symmetry this time, which is pretty nice. Maybe we should exploit that. So you might notice that this function has y-axis symmetry, because if you replace x with minus x, then you get the same expression back. So we can really just test this interval for x less than -2, and it will be the same behavior as for the interval from 2 to infinity. So in that interval, my favorite x value is x equals to -3. And if I test there, I get -3 all squared minus 4 divided by -3 squared is a positive number, right? 9 minus 4 divided by 9 is 5/9, which is positive. We get the same exact value over here when we test x equals to 3 by that y-axis symmetry of this function. So we get to put plus signs in both of these intervals here. Okay. Next up is the interval from -2 to 0, which again, by that y-axis symmetry, should have the same behavior on the interval from 0 to 2. So I'm going to test over there x equals to -1. And -1 squared minus 4 divided by -1 squared, I think is like 1 minus 4/1. That would be -3, which is negative. And we get the same exact value when we test x equals to 1, again, because of that y-axis symmetry. So both of these intervals have that the function in question is negative on that interval. So then what was it they were looking for again? They were looking for the x values where x squared minus 4 divided by x squared was strictly negative. Oh, and that is exactly these two intervals. And notice we are not going to include 0, because 0 is a place where this rational function is undefined. So our solution is 2 intervals, the interval from -2 to 0 union with the interval from 0 to 2. Okay, next up is this one. This is particularly fun. I like this one a lot. We have x squared plus 1 divided by x squared plus 7, and we want to know when is that strictly bigger than 0. Well, if we try to solve, if we set the numerator equal to 0, we get x squared plus 1 equals to 0. Well, x squared is always bigger than or equal to 0, and then adding 1 to that gives us something that's always bigger than or equal to 1. So x squared plus 1 is never equal to 0. And oh, also, x squared plus 7 is never equal to 0 by the same logic, right? If we take any number and square it, we get a number that's bigger than or equal to 0, and then adding 7 to that gives us a number that's bigger than or equal to 7. So here then we have some number that's always positive divided by some number that's also always positive. And think that that fraction then should always be positive, because it's a positive number divided by another positive number. So in fact, since we get no x values of interest, we can really test any x value we like. And if we test x equals to 0, it's another way to see this, we get 1/7, which is positive. So in fact, every x value we could put into this gives us a positive number out at the end. So the solution is the interval from -infinity to infinity. Okay. And let's see, I think there's 2 more examples here, but I think those right now that we've done are good enough. So if you'd like to watch, we'll talk about this next one a little bit because it's a little bit different. But yeah, I mean, in here it's probably good enough. So let's do this one and then call it a day. So we have 3x minus 2 over x minus 4, and we want to know when is that bigger than 3? Well, maybe we'd rather have 0 be on this side, because then we can employ the sort of technique that we've been using all along to determine that if a function is not equal to 0 and it is defined somewhere, then it must be either positive or negative, right? So let's first subtract 3 from both sides. And so we'll have 3x minus 2 divided by x minus 4. Then all minus 3 is bigger than 0. Well, now I'd like to get a common denominator because I don't like having to deal with these two separate terms here. So the common denominator should be x minus 4. So I'll multiply 3 by x minus 4 and then divide that out. So I get the same thing here. So that 3 becomes 3 times x minus 4 divided by x minus 4. Okay, but then 3x minus 4 becomes really 3 times x minus 4 really becomes 3x minus 12. And then if we subtract all of that from 3x minus 2, we really get 3x minus 2 minus 3x and then plus 12. Where does this plus 12 come from? Well, we have minus out here and 3 times minus 4. So it's really minus 12, which is plus 12. So when we combine these two fractions, we really just get 3x minus 3x, which is 0, plus 12 minus 2, which is 10. So we really get 10 over x minus 4 is bigger than 0. That's the inequality that we want to solve now. And this one's not so bad. There's no zeros of the numerator, right? Because there's no x in the numerator, and 10 is certainly not 0. So the numerator is never 0. And the denominator is only equal to 0 when x equals to 4. So there's really only one x value of interest here. So we're really just going to break the real line into two pieces. The x value is less than 4 and the x value is bigger than 4. So when x is less than 4, I like to test x equals to 0. And I get 10 divided by 0 minus 4. That's 10 divided by minus 4. That's a negative number. And for the x values bigger than 4, we'd like to test x equals to 5, let's say. And so we get 10 over 5 minus 4. That's 10 over 1, which is positive. So this function looks like it is less than 0 for x less than 4, and it is bigger than 0 for x bigger than 4. It is undefined when x equals to 4. They were asking us about when is the function in question bigger than 0. So we will pick the right side here. It is the interval from 4 to infinity, not including 4. OK, now I really think we've done enough for today. So if you'd like to see the last example, we can talk about that maybe when we meet in class time, or we can talk about it via email. So we'll see you later.